Today I wanted to start a new topic, the last in this course. It is the heat equation. So what is the heat equation? It describes the development of the evolution of the temperature distribution in homogeneous medium. So suppose we consider some medium, say some material, solid material in filling some domain or maybe the whole space. It is one or two or three-dimensional material. And suppose its temperature is a function theta of x and t. X in some Rn, no, physically n equals 1 or 2 or 3. Now, here we have the temperature, and what we know that the heat energy is flowing from the points where the temperature is higher to the spots where it is lower. Yeah, and if so, it flows in the direction of decrease of temperature and the direction of its gradient, but it's proportional to minus gradient. So the heat flow Q of xt equals minus some coefficient A times gradient theta of xt. Yeah? Now, if the flow moves somewhere, then its temperature changes. So the temperature is the energy content of the unit of volume is proportional to the temperature, no, to some degree, say proportional, with some coefficient. This coefficient is called the heat capacity. Yes? C, heat capacity. Of the medium. Yes, and so this means that heat, the energy content is proportional to the temperature. Energy content E of xt, energy per unit volume. So E equals C theta. Yes, C, this is called heat capacity. And so if we have the flow of the energy, then it can have some divergence. It can be positive or negative. And the divergence is, so the temperature grows proportionally to this divergence. So d theta dt equals minus 1 over c divergence of Q. Yes? Equals, and Q is minus A gradient theta, equals A divided by C, divergence of gradient theta equals A over C Laplacian of temperature. Yeah. So now let us write simply d theta dt equals some coefficient k Laplacian theta. This is the heat equation. Now, this same equation describes many other processes. Say the same equation describes diffusion of additive in, say, liquid or gas or even in the solid. So we briefly study this equation, how to solve it and what are its basic properties. Now, for simplicity, let us assume that k equals 1. For generic k, we can transform it to this by changing the, say, scale of time or of space. Yes? So k equals 1. So our equation is d. And to go away of a specific problem of heat temperature, because for diffusion it will be other variable, we simply write du dt equals Laplacian u. U is u of xt, x in Rn, t in R. Yes, so here we have this full problem, and so we are studying this problem. So our equation is du dt equals Laplacian u. Now, the simplest case is one-dimensional, when u is a function of xt and x is on the line. It is already a very interesting problem, I would say. No, physically, sometimes usually we talk about, say, a thin rod or wire and consider the propagation of heat along this wire. But more realistic is that we have a layer of something, so the temperature depends, say this is a wall of the building, yeah? So here is outside, here we have the temperature 1, here is inside temperature 2. We have different temperature inside and outside. And so something interesting happens inside this wall. If, as usually, say like now, the temperature inside is more than outside, so the heat is going from inside to outside, and it results in some distribution of temperature which may depend on time. And it depends on one variable which is transverse to orthogonal to the wall, and usually the size of the walls in the vertical, this horizontal direction is much larger than the size in the direction orthogonal to the wall. So can neglect derivative in these directions and consider only the normal derivative. So we have one-dimensional problem. Now we have, for example, interesting problem that the temperature outside changes periodically. Usually temperature at night is lower than in the day. So here we have, say, periodically changing temperature. Here we have more or less constant temperature, and so how it looks inside the wall. If time permits, we can consider the problem like this. So consider the case n equal 1. N equals 1. So the equation looks as follows. du dt equals d2u dx squared. And we are going to solve this problem. For the heat equation, we consider from the beginning the initial value problem. Initial value problem. So we have the equation and the initial condition u of x at time 0 is a given function f of x. Yeah? So we have this initial value problem. We can draw it in the xt place, plane. So we give initial condition on the axis t equals 0, and then consider how it propagates. This is already non-trivial problem. But we have already experience with the wave equation and Laplace equation. So in both cases, we have the following thing, that it is worthwhile to consider initial condition when I would call it fundamental solution. So consider the most elementary, the simplest initial conditions in our sense, when it is just delta function. So u t minus u xx equals 0, and u for t equal 0 equals delta of x. So all the temperature is concentrated here initially, and then it somehow propagates. So it corresponds to the following situation, that we had absolutely cold medium, yes, and at t equals 0, we transfer to this medium a unit amount of energy just in one point. So it looks like we, say, explode, say, atomic bomb in the origin, something like this. And then the effect of this explosion propagates. Yes, and we consider just the heat effect, not the mechanical effects. So what will follow after it? So here should be, for t positive, we should have something like this, that the heat propagates, yes. If you take further line, then we have more diffuse distribution of temperature. So this one point gives rise to some spot, which spot will become farther and farther, and the integral of theta of u should stay constant, because the energy simply redistributes along the line, but does not vanish and does not appear from nothing. So we have to find this. And solution of this problem, fundamental solution, let us denote it k of xt. Yes, k of xt. And our goal today is to find this solution. So let us start. No, I am not the first mathematicians who solved this problem, so there was enough people who did it before me. So no, I know the answer, but I want to show the way how to find it. So after several trials and errors, we are looking for solution. Let me look for solution. K of xt having the form k of xt equals t divided by it's like t to the power, one moment, I forgot. Say 1 over t to the power alpha, some function v of x divided by t to the power beta. Now here we have two parameters alpha and beta. We have to find them and find this function v. So let us substitute this into the equation. So k of xt equals t minus alpha. No, here we can always multiply it by constant and find the constant so that it will be true delta and not some delta with coefficient. V of t minus beta x. So kt dk dt equals minus alpha t minus alpha minus 1 v plus t minus alpha times v prime. No, I don't write, the argument will be always this. Times derivative of this minus beta, t minus beta minus 1 x. It is derivative of this with respect to t. Equals minus alpha t minus alpha minus 1 v minus beta t minus alpha minus beta minus 1 x v prime. Now differentiate it with respect to x. Kx equals t minus alpha v prime of this times t minus beta. Yes, kxx equals t minus alpha, okay, equals t minus alpha minus beta v prime minus alpha minus 2 beta v double prime. Yes, so our equation is minus alpha t minus alpha minus 1 v minus beta t minus alpha minus beta minus 1 x v prime minus t minus alpha minus 2 beta v double prime equals 0. Now we want to have, let me denote this combination x divided by t to the power beta equals, say, r. Yes? Now what we can do, we can divide by t minus alpha minus 1, it is minus alpha v minus beta t minus beta x v prime, yes, minus t minus alpha minus minus beta plus 1 v double prime equals 0. Alpha minus 1 minus yes. Yes. Now, one moment. Minus 2 beta plus 1. Yes, and now let us look. Alpha and beta are in our hands, so we can simplify it. Let us take alpha equal beta equal 1/2. Yes? So we have the following equation. Multiply by minus 1. 1/2 v of r is this, plus 1/2 t minus 1/2 x v prime of r plus t. So if alpha and beta equals 1/2, then this is 0 plus b double prime of r equals 0. Now beta is 1/2, so x divided by t to the power 1/2, and here we have the same combination, x and t minus 1/2. Yes, so this is r. So we have equation 1/2 v of r plus 1/2 r v prime of r plus v double prime of r equals 0. Now we see that this is 1/2 v of r plus r v prime of r is nothing but a derivative of r v of r. Prime plus v double prime of r equals 0. Now let us go further. We have derivative of this and second derivative, so we write r v of r 1/2 plus v yeah, 1/2 r v of r plus v prime of r. I integrated once. Equal, no, it should be equal c, but let me shorten the way and say it is 0. Let us see what we get. Simply because v should go to 0 when r goes to infinity. So it happens if here is 0. So we have v prime of r plus r over 2 v of r equals 0. Now the first order linear equation and the solution is v of r equals c e to the power integral r over 2 dr. Yes? Which is equal to c e integral r over 2, it is r square over 4. R square over 4. And now, so we have it, this function v. And our solution, I mean fundamental solution. Now we can forget about this. K of x xt equals t to the power minus, no, some constant c, t to the power minus 1/2 v of x divided by t to the power 1/2. Yes? R is x divided by t to the beta, beta is 1/2. Equals ct minus 1/2 e to the power, I'm sorry, e minus, of course, minus r x square divided by 4t. Yes? So again, k of xt equals c t minus 1/2 e to the power x squared divided by 4t. It remains to find this constant c. So this constant c should be such that the integral of this function along the x-axis for x for any fixed axis, integral should be equal 1. No, by the way, we have to prove that it is equal 1 and the same constant along every line x t equal constant. To this end, let's find integral over the whole line from minus infinity to plus infinity k xt dx. What is this? Equal c t to the power minus 1/2 integral from minus infinity to plus infinity e minus x squared divided by 4t dx. Let us concentrate on this integral. So, integral minus infinity to plus infinity e minus x squared divided by 4t dx. Now, first of all, let us get rid of this t. So we write x divided by 2 square root of t equals, say, y. X equals 2 square root of t y. Dx is 2 square root of t dy. Yes? So this integral equals 2 square root of t, integral from minus infinity to plus infinity, e minus y squared dy. So this way we got rid of dependence of t. So we have just one integral. So let me write I equals integral from minus infinity to plus infinity e minus y square dy. Now there is a trick, possibly you learned it in the calculus, but if not, I will show you. This integral, it is not see, we cannot treat it, find it directly. But let us consider the multiply this function. Consider function f of yz equals e minus y square times e minus z square. Yes? And let us find double integral. Integral from minus infinity plus infinity. Integral from minus infinity to plus infinity. F yz dy dz. First of all, the function f is product of function of y and product of function z. So it is integral of minus infinity to plus infinity e minus y square dy times integral minus infinity to plus infinity e minus z square dz. No, this is just what we are looking for, I. And this is I, which is equals I square. It's on one hand. On the other hand, f of yz equals e minus x square plus y square equals e minus r square, where r is polar coordinate. R, if you go to the polar coordinates, yes, this is r, this is theta. So it is the function depending only on radius, so it's natural to go to polar coordinates. So integral f of yz dy dz equals integral from 0 to infinity 2 pi r times e minus r square dr. And here this 2 pi means that we integrated already by theta. So the area element in the plane is 2 pi r dr. 2 pi r dr d theta. The theta does not depend on theta. Integral from 0 to 2 pi e minus r square times r d theta dr. Now we integrate over the theta equals integral from 0 to infinity. This integration gives us 2 pi r e minus r square dr. Now integral this equals 2 r e minus r square dr equals d e minus d e minus r square. Yes. So if you differentiate it e minus r square, you have this 2 factor 2r. And so equals minus pi e minus r square r 0 to infinity. At 0 it is 1, at infinity it's 0. Now it is minus, so it is this equals 1 equals pi. In short, it is equals pi. So on one hand. On the other hand, it is equals I square. Equals I square. Square of our integral, which we are looking here. Yes? So I equals square root of pi. Yes? This well-known result. Now we have k of xy equals ct minus 1/2 times 2t 1/2 integral from minus infinity to plus infinity xt dx 2t 1/2 times square root of pi. Yes, so c times 2 square root of pi equals 1. Because we want that this integral k should be 1. It is 1. C is 1 over 2 square root of pi. Yes? And at last we can write our function. K of xt equals 1 over 2 square root of pi square root of t, 1 of square root of t, it is a constant square root of t, e minus x squared divided by 4t. Yes? Because we had this function. Equals, no, it can be written as square root of 4 pi t e minus x squared divided by 4t. So this is our fundamental solution, and we have already proved that integral minus infinity to plus infinity k of xt dx equals 1, because t dropped from this integral somewhere in between. T, we lost t, here it was dropped. This integral here t minus 1/2, but the integration gives t 1/2. So it dropped here. So what are the properties of this function? No, first thing is that k of xt is positive, strictly positive for t positive t. Yes? No, because this function it is exponent of something which is exponent is always positive. Second, kxt, if you look, it is defined by this formula, so it is infinitely many times differentiable function. In fact, it is even analytic function, but for now it is very good smooth function. 3, that this function decreases fast. Yes, this means this exponent, yes, for any t positive, it decreases faster than simply exponent. It is e minus x squared. So it decreases faster than e to the power something constant times x. Yes? So I would say k of xt decreases fast as t model t goes to infinity. So for now, the next property is the following. So, so this function is the product of two terms. One term depends only on t, this factor. So this factor depends, in fact, of combination x squared divided by t, or x divided by square root of t. Yes? So, and this means that integral k of xt dx from minus say a t a square root of t to a square root of t depends only on a positive constant. Yes? So what does it mean? Consider this function. It is this function for say t equal 1, this function. So it is minus a, this a. Now what happens if here is t equals 1? What will happen if we change t, take some other t? Then this function it shrinks or stresses with coefficient t all this function. Yes, so our function has the form k xt equals say c t minus 1/2 v of x t minus 1/2. Yes. So for t small, this shrinks. Yes. For t large, this expands, but all it is multiplied by argument x multiplied by constant parameter, and so the total integral is 1. This means that what happens, say when t goes to 0, this shrinks. Yes, so we have this, but it's multiplied by larger factor, t minus 1/2. Yes, so we have this picture, and these bounds also shrink, but minus a t 1/2, this a t 1/2, these two bounds, but the integral between them will become the same, remain the same. Yes. So this function, let us call it, depends only on a. So let us define this function, say g of a equals g of a. Yes? So this function. So what can be said about this function? That this function for a equals 0, it is 0. Yes, for integral from 0 to 0. When a grows, it grows. And for a goes to infinity, it goes to 1. No, it tends to 1. Yes? So we have it, and this rate of this how close it becomes to 1 is very high, because this function k, you see, it is e minus exponent x squared. Yes, so this function decreases very fast, and so its integral, no, its primitive function grows, but very slowly. And this means, so what happens when the t goes to 0, xt, then if you take, say, a such that this integral is close to 1, or say 0.99, then this for any t, if you mark the points a square root of minus a square root and a square root, such that integral along this segment is, say, 0.99, and if you do it for any t, then we have this parabola. Yes? So its length, it is t, it is the length is a square root of t, no, from minus a square root to a square root of t. Yes? So this means that the mass of this function concentrates to 1.0 when t goes to 0. Yes? And this means the next property, okay, let me write it here. K of xt goes to delta of x as t goes to 0, approaches to 0 from above. Yes, t goes to 0, and this function, say, becomes closer and closer to delta function, like this. No, it is easy to do it more rigorously, but I don't want to overburden you. And this gives us the following formula, that if this function k is a solution of initial value problem, that for at t equals 0 it is delta function, then we know how, using delta function and shifted delta function, we can make any other reasonable function. So we know that for any function f of x is integral f of y delta of x minus y dy. Yes, so we have the function delta of x minus y multiplied by f of y, then integrated with respect to y, and the result will be the function f of x. Yes, so all the function is the sum of delta functions, which we put infinitely close to. Yeah, sorry, it was some technical problem. So we have this formula, and now we can, using this formula, solve the general initial value problem. So ut minus uxx equals 0, it's our equation. U for t equals 0 equals, say, f of x. This is our initial value problem. If in space f of x were delta function, then solution will be kxt, because it goes to delta function and as t goes to 0. And now we can say make any function from shifts of delta function by this formula, and correspondingly we have the formula for solution u of xt equals integral from minus infinity to plus infinity k of x minus yt fy dy. It's a similar formula. We had such formula for string equation, we had it for wave equation, for Laplace equation in half plane or even in half space. Yes, and so we have similar formula for the heat equation. Now, next time we consider the consequences of this formula, how it can be used and what it means. We consider it next time. For now, let us finish. Have a good time. Bye.